So as you can see in the chat room, we have uploaded the links, and if you are going through Java and such, please keep in mind you have to install Java first. Okay, I got a couple of messages saying um, I can't run the software and so on. Install Java and then go for the OpenRocket software. So, sir, shall we start? Because we are 34 and counting upwards. So,
Sounds good. We'll start.
okay. So, ladies and gents, welcome to the fourth installment of the Model Rocket workshop organized by SEDS Mora and SEDS SLTC. And with today's session, we actually conclude the workshop series for the first series. And today we have a regular person as our guest speaker, Mr. Josh Frizzell, who gave an introduction on model rockets. Hello, sir. Good evening, and to everybody in Sri Lanka, good morning. So, without further ado, you are not here to listen to me. So, Mr. Frizzell, the floor is yours. I believe you can share your screen and videos now. Yeah.
Okay, we'll get started. Again, of course, this is the introduction to open rocket design software. So in the first few sessions, we've been talking about things like center of gravity, center of pressure, thrust to weight ratios. Open Rocket is a software that's going to help you design a rocket to make sure that it's stable when it flies and it's safe to fly. It'll tell you how high the rocket's going to go, how fast it's going to go. You can gain a lot of important information about how you need to set up the rocket and make sure it's going to fly safe and fly the way you want it to do. So let's get started. Um, this presentation is going to be geared for beginners. I'm going to start from the very beginning from a clean slate. I'm basically just going to go through setting up a basic small rocket in the software. We'll get a little bit more into some staging and things towards the end of the presentation. If you're a little bit familiar with the software, this might feel like a bit of a slow start, but we're going to start from the very beginning just to make sure everyone's on the same page. It's hopefully kind of an interactive thing when you're learning a software. If you get a little bit behind, then you're sort of behind through the whole presentation. So maybe pop a question in the chat. Hopefully I'll see it and I can address it as we go. But yeah, let's get started. I'm going to share my screen here. All right, so this is the Open Rocket interface. When you first open the software, this is probably what it will look like. So if you've just downloaded it, you're not familiar with it at all, it'll be just a little executable Java file. You double click on it and it'll start up. And this is what you should see. It may or may not come in with English units. When I download it here in the United States, it comes in English units, and that's what I'm familiar with. But I'm going to switch this over to metric units. So I think that's probably what most people are going to be most comfortable with. So that's what I'm going to do first. To do that, I'm going to go up here to edit. And then I'm coming down to preferences. And again, if I'm going painfully slow, I apologize, but I'm gearing this to the beginner here. But again, we're going to edit down to preferences. I'm going to go to the units tab, and I'm going to switch to default metric. So it changes everything to metric there. So we're going to close that. Sometimes it makes you restart the software to make those settings take effect. I'll get started here, and if it necessitates that I restart it, I will, but I'll get started. Basically, I'm just going to enter in the design, parameters of the rocket. I'm going to start from the tip down, starting from the top down. So we'll do the nose cone first. Where we want to start adding parts, we're going to have this rocket design tab active. So there's rocket design, motors configurations, flight simulations. Those tabs come later. first we have to build the rocket, right? So we're going to go to this design tab right here, rocket design. Okay. I'm going to select the nose cone first. So when you select these parts, you click them once. If you double click them, it'll give you 2 parts. So you just need to click it once. So I'm going to click nose cone. And you see I've got my parts tree or my parts list over here on the left. And a window opened up. It looks like it's working in metric, so that's good. That's what I want. And again, we're just going to be designing a small rocket. Again, we work here in English units in the United States, so forgive me if I sort of stumble through the metric units a little bit. But let's go to, first let's look at this general tab. We've got the nose cone shape, and it says ogive. And ogive is just the intersection of 2 circles. Very simple shape. We've got other options here. There's a drop down. Conical is a cone. Ellipsoid, several other, common ones. Hack series is one that's used in a lot in, high power rockets and things. But we'll just go with ogive. That's a simple one. It's probably what you're going to see. Like if you buy a simple kit and it's got a little plastic nose cone with it, it's probably going to be an ogive. So we'll go with that. The nose cone length. I have a little rule here. I'm going to be referencing to, again, a small rocket. This is sort of like what I'm going to be entering into the software. This is a good place to start, something small, this size. So that's basically what I'm going to be building as we go along. Okay, so for the length here, I've got 70 millimeters. Anytime there's a unit in Open Rocket, you can change the unit manually. So we kind of set the whole default thing over to metric, and you can individually manipulate each unit too. So for here, like for example, for nose cone length where it's got centimeters, I can just click the unit and it gives me a list that I can choose from. If I choose millimeters, right, I can make that whatever I want. Just double click it and highlight it, right? So put that in there, go to the next thing. I'm going to be making a rocket that is 24 millimeters in diameter. So the base diameter, I'm going to put, I'll do that millimeters just to keep it consistent. All right, so now I've got a nose cone 70 millimeters long, 24 millimeters diameter. That's going to be pretty typical if you buy an entry-level kit. Wall thickness, that's about right. We can also select the materials. Now the materials are important because the rocket's software is actually going to be calculating weight and balance parameters for you. If you were with us on the last presentation, you know that the center of gravity is important when you design for stability, and the density of your materials is important for the software to be able to accurately figure that out. So we're going to go over here to component material. We select the drop down, have a bunch of choices. I'm going to go with a plastic. That's what is going to come with, say, an entry-level kit. So I'm going to choose polystyrene. It's a plastic. And I'll leave the regular paint. So quick little recap. We've got the nose cone set at 70 millimeters long, 24 millimeters diameter, and we selected it as plastic. All right. So we're going to move over to where it says the shoulder. Select that shoulder tab. Now, what's the shoulder? So the shoulder is when we've got the rocket, the nose cone. If you recall from our last presentation, when we want to deploy our recovery device, like our parachute or our streamer, we're going to have a little explosive charge associated with the motor that's going to pressurize the inside of the body tube and push the parachute out. So this nose cone has to be able to pop off. So it comes off like this. There's our streamer inside, right? But the shoulder is the back end of the nose cone, this part that slides into the body tube. So basically the outer diameter of the shoulder is the same as the inner diameter of the body tube. So it just slips in there with a little bit of friction, right? So the shoulder diameter is going to be just inside the inner diameter of the body tube. I'm going to set this to 23 millimeters. So it just barely fits in there. The length on this particular one is 1 centimeter. right? And we'll make the plastic consistent with what we had in the other, the pointy part of the nose cone. We'll call that 0.2 centimeters. Okay, so if I move this window out of the way, we can see we've got the nose cone there. We've also got the shoulder added. That's the part that's going to slip into the body tube. Okay, so we'll call that good. Again, questions, try to, get my attention in the chat or whatever you need to do. All right, so we've got the nose cone. Next thing we're going to add is the body tube. So that's kind of the main, fuselage part, if you want to call it. That's this long tube part that makes up the main body of the rocket. Okay, so to do that, we're just going to click body tube one time. And if you accidentally do it twice, or you have something you want to get rid of, I'm going to add some extra stuff there that I don't want. You can just come over to this parts tree on the left, and I've got highlighted any part. And if I hit delete, bye-bye, it's gone. Okay. So now we've got what we want. So this, you see the software has automatically selected the correct diameter for the body tube. It basically just matched it up to the part that it goes behind that you've added it to. That's why we work from the top down. The software just kind of flows that way. So I'll show you how to add in parts and move them up and down the tree later. But if you start from the nose cone and work your way down, that's the easiest way to go. But this body tube on this rocket is 22 centimeters. So if you want to get in and manipulate measurements on any part, you can either click on the part down here in this diagram, or you can click on it over in the parts list. So if I click on it down here in the diagram, if I double click down here in the diagram to select it, I get a window and I can add some more information, change things around. Again, the length on this one is 22 centimeters, so I'm just going to add a couple centimeters there. The outer diameter, it's already selected that for me because it matched it to the nose cone, right? Inner diameter, same thing. Now this one is cardboard. It's already by default, it's got the cardboard selected as the material. That's what I want because that's what this tube is made of. It's just a very thin cardboard that's spiral wrapped in a couple layers with some adhesive. Makes a great little body tube for a small rocket. Okay, so that's all set. I'm going to close that. I'm going to go ahead and save this. Just good habit to be in, just save things as you go so you don't lose all your work. But it's taking a little while to save here. I think I might have froze up, unfortunately. There we go. I'll just put I'll call mine sample rocket for now. So I've got it saved. So we've got our body tube there. If you recall from the last presentation, we need to have a motor mount. So our motor is going to fit into the rocket. We need to make sure that the motor can't push its way out forward through the rocket and actually shoot through the rocket, right? So we need a way for the motor to transmit its thrust to the rest of the main body rocket. We also need to make sure we have a retention going to the rear to make sure the motor doesn't eject itself out the back when the ejection charge goes off to pop the parachute, right? So the motor mount, its purpose is to keep the motor aligned with the body tube of the rocket and also make sure it can't shoot through the rocket. It stays attached or fixed into the rocket, right? I'm going to show you a couple examples of that. This is a small black powder motor. If you recall, we talked about some different types of propellants. There was black powder, ammonium perchlorate composite. We talked about rocket candy made of sugar and potassium nitrate, etc. This is what a commercially available motor would look like. This is a black powder motor, really typical of, good one to start out on for beginners. Okay, so here's an example of a rocket. I'm looking at the back, right? So there's the side, there's the back. This is the motor mount inside. There's kind of two concentric tubes, and the smaller one on the inside is the motor mount, and it's held in, glued in with some rings around it, and then the motor will just slide in there. Okay. And you see, if you can see, there's a little clip there that holds it in so it can't pop out the back. Okay. But that's the motor mount. That's what we're going to add next. Okay. So In Open Rocket, when you want to add parts to another part, you can first select the part that you want to add something to. So let's see how that works. So I'm going to add a motor mount to the body tube. So first I'm going to select the body tube. And again, you can either do that down here in the diagram or over in the parts tree. All right. So I selected the body tube. And if you noticed when I did that, several other parts that were grayed out and not available, now they are available. So I'm going to select right here where it says inner tube. I'm going to click that one time. And you see it's added an inner tube here. Now, very important, you need to tell the software that this is a motor mount. Otherwise, it's just going to count it as a regular tube. You're telling it that this is a place where a motor can be installed. So to do that, you see right now we're on the general tab. We're going to go over to the motor tab. And this is a really important step. If you don't do this now or at some point, you won't be able to install a motor and you won't be able to run the simulation. So we're going to go to motor and we're going to hit this checkbox where it says this component is a motor mount. All right, that's an important one to get. So let's go back to the general tab again. Make sure you've hit this motor tab. Make sure that checkbox is checked. We're going to back to the general tab. We're going to set this up as a standard motor. 18 millimeters is a standard commercially available motor size. So that's what we're going to set this up as. It's already got it by default in this case, but you could change it if you wanted to. Again, you can change the units to anything you want. You can change the outer diameter, inner diameter. It's already got the inner diameter set at 1.8 centimeters. So that's already a standard size. We're going to keep that. And it's already a pretty realistic length, but if we wanted to change that, we could. Okay. We also see that it's got the position relative to the bottom of the parent component. So remember, we added it to the body tube. So the body tube is the parent component. That's what we're adding this new inner tube to. And we can move it back and forth up and down the rocket by adjusting this where it says plus. Right now it's at 0 centimeters, but you notice if I change that, okay, it's moving and it's measuring from the tip of the nose. So if I add a positive number here, it's moving it back away from the tip of the nose cone, right? If I go down, it's actually moving it forward. So there I'm at -4, it's moving it forward. I'm gonna put it back to where it was. I'm gonna put it so the back end of the motor tube is flush with the back end of the body tube. So we're gonna set that back to 0. Okay, so that's where we want it. And they've already got the cardboard material. That's what this is made of. It's just a little cardboard tube. Okay, so that one is in good shape. So I'm going to close that, save it. Okay, so we've got the motor tube in there, but it's right now it's just in there loose. We need to affix it to the rest of the rocket, right? So again, I'm going to add some centering rings in there. So there's these rings that go around the motor mount, and they will glue the inner diameter to the motor mount, and the outer diameter of the centering ring will glue to the body tube. So the motor mount is fixed in place. So to do that, I'm going to, again, highlight the body tube because I'm adding parts to the body tube. And I'm going to select centering ring, click it one time. It's already got, by default, it's got the diameters all set. I'm going to actually increase the outer diameter a little bit. Make that 23, a little more realistic. Okay. So if you saw the centering ring outer diameter increased a little bit so that it's going to touch the inside of the body tube, we're going to glue it in place. Okay. It's already got the inner diameter correct so that it would glue to the motor mount tube. And the position we're going to change a little bit. So I'm going to take this one, I'm going to move it up towards the front of the motor mount tube. We're actually going to put 2 of them in there so it stays centered. But in this case, again, we're moving, the measurement is away from the tip of the nose cone. So since we want to go closer to the nose cone, we're going to go down to get a negative number. And you'll see it move forward as I do this. But if I click the down arrow here a few times where it says position relative to bottom of the parent component, I've moved it up to the front basically. Okay. So that one is happy. Now, if we don't want to go through all that mess again, we can actually copy the part and just put another one in there. So I can go over here to my parts list. I can highlight centering ring, and I can go to edit and choose copy, and then just go again to edit and choose paste. And now it's made an exact copy of it, and you can't see it down here in the diagram because it made an exact copy of it. It put it in exactly the same place. So we can move it back, farther back. I'm just going to double click this over here in the parts list. We get our window pop back up, and I'm going to come down here to where it says position relative to bottom parent component. We're just going to change the position of it. And when I do that, you'll see it move back. Okay. And I'm going to leave that at about -2 centimeters. The reason for that is if we want to use this rocket in a multi-stage configuration, we're going to want a little bit of space behind the back centering ring. You'll see how that fits together towards the end of the presentation. But for now, just realize that we don't want that back centering ring all the way to the back because it won't give us any room to attach our booster stage. Okay. So we've got 2 centering rings in there. We've got the motor mount secured to the body tube. That's good. Those would all be glued together. Make sure those are secure. That's kind of a safety critical part. Make sure the motor can't shoot through the rocket. And then you've got this out of control motor and flying all over the place with the rocket still sitting on the launch pad. Okay. So you got the motor mount tube, you got the 2 centering rings. That's all glued into the body tube. All right. So we'll close that. And now if you recall, we talked about thrust rings in the first session a little bit. That again, that's what the motor is going to push up against. I have a smaller one, a smaller rocket here. Let's pull that motor back out. Okay, so inside this one, there's another small cardboard ring glued up inside here, and it's glued at a position where if I put the motor in there, it will slide up to a point, but then it stops. That's as far in as it will go. So as this motor generates thrust, it's actually pushing on that ring that's glued inside about right here. Okay, so we're going to add that next, the thrust ring. So the motor has something to push against. Okay, so inside the motor tube, we're going to add the thrust ring. And the software, they call it an engine block. But if we select the inner tube here, remember, if we select a part, we can add other parts to it. I've got the inner tube highlighted. I'm going to select engine block. Okay. Now it put the engine block all the way at the back. That's no good. We don't want that because then we couldn't fit a motor in there at all, right? So to adjust the position, one thing we can do is we can change this position relative to, instead of bottom of parent component, I'm going to change that to top of parent component. And then change this to 0. So there you see it moved it up to the front. So now we're measuring from the top of the motor tube, set it to 0, it moves it all the way up to the front. That's what we want. So we can fit our motor in there, right? All right, so I'm going to save that. And we've got our nose cone, we've got our body tube, we've got our motor mount all set up. Now, this rocket's going to have a problem. If you recall, we talked about in the first session, flight stability. We want to design the rocket so that it will fly straight just based on the shape of it. If it gets perturbed, hits a little air turbulence, it will actually correct itself and get back on track all by itself, just by the shape. And we said that compared to the center of gravity, we want to have the center of pressure behind the center of gravity. So in this case, on this design, we've got a problem. So we've got our center of gravity here, which is indicated by this blue symbol, and our center of pressure over here, which is indicated by the red symbol. Now, the center of pressure right now is in front of the center of gravity, which is no good. If we look over here where we see stability, we are at negative 4.9 calibers. So what that's telling us is, compared to the body tube diameter or the caliber, the distance between the center of gravity and the center of pressure is 4.9 times the diameter of the rocket and the center of pressure is in front of the center of gravity. That's no good. We need to get the center of pressure behind the center of gravity to make sure the rocket is stable. Okay. So how are we going to do that? Well, in most, let's say amateur rockets, we're going to do that with fins. Okay. We're going to move the center of pressure back to make sure the center of pressure is behind the center of gravity. We're going to do that by adding fins. So to do that, let's select the body tube, okay, because we're going to add some parts to the body tube. I'm going to go up here to this one called Freeform. I'm going to click that once. And I get this window that I can modify the fins and change different parameters of them, change the shape, change how many. Right now, by default, it comes in at 3. I can change that up. If I want, we need at least 3 for a stable rocket, but we can add it up to 8 in the software. So I'm going to increase that to 4 just to give you an idea of what that looks like. Again, if I change that number, you'll see it changing from 3 to 4 fins. Okay, that's what it would look like with 4. Here where it says cross-section square, that's like if you were looking at it edge on, like this. There we go. This surface, right, that meets the air, if that's just flat squared off, that would be square. If we sanded that to round it off, make it a little more aerodynamic, we can select rounded. Really, that's probably what you'd want to do if you were actually building this thing. So I'll change that to rounded. And we can change up the shape. So if right now we're in the general tab, if we go over to shape, we can basically manipulate this however we want. It's got these little boxes that we can grab and drag around. So if I grab this one, you see as I move that, it's changing the shape of the fin on the model, right? You're also seeing that the stability now is up to 2.36 calibers. If you recall from our last session, we want to try to get that between 1 and 3. Right now it looks good, but we haven't added a motor in the back yet, which is the most massive heavy part that we're going to add, and that's going to shift the center of gravity way back. So we'll have to kind of reevaluate this after we put a motor in it. But right now it looks good, right? And you'll notice as we change the shape of the fin, the stability is going to change. So if I move the surface area, farther forward, you see that we're, affecting the stability, right? So these shape changes are going to change the stability because changing the shape of the fins or how many fins we have is going to change the center of pressure, which affects the stability of the rocket, right? So we'll leave that there for now. I want to talk a little bit about fin tabs. It's kind of important, not super critical in the low power world, but once you get into high power, you're really going to want the fin tabs. Use what we call through the wall fin mounting. So I'm going to touch on that just a little bit. If we select this fin tabs tab, I like that. We get a few different options. So let's look at, we've got the fin tab length, but let's look at a couple of the other ones to make it so that you can see what's going on. So what we're actually doing is we're taking the fin and making a tab that will go through the body tube. So we would have to cut a slot in the body tube as we build the rocket, and it'll actually glue the fin to the motor mount. So it creates a much stronger structure for the fins. If you just glue the fins onto the surface of the rocket, it'll work for low power stuff, but fairly easy to break off. If we put a slot in the body tube and have this tab go through the body tube and attach, we can glue it to the motor mount and glue it to the body tube, we end up with a much stronger structure. So let's do that. I'm going to change this to millimeters so I can sort of sneak up on it. But if you watch over here where the fins are, you'll see this tab growing down from the fin. And we want to get that just to touch the motor mount. So it would glue, probably go like 2.5 here. So you'll see that tab we've added, it's going through a slot that we would cut in the body tube, and now it touches the motor mount, we can actually glue it to the motor mount. I want to make it not quite as long because I do want some surface attachment out on the outside of the body tube. We just want a slot where that tab will go down inside. I'm going to make the tab not quite as long. That would be pretty typical. So again, we would cut a little slot in the side of the body tube. This little tab is part of the fin. It would go through the slot and then glue to the body tube. Excuse me, it would glue to the motor mount. And we've also got glue surface on the outside, on the front, and on the back. So that ends up with a really strong joint. When you set these up like this, if you have a hard landing, that fin is going to crack off and break. The wood itself is going to break before the joint fails. So it's a very strong joint, okay? So I'm happy with that. We'll keep that. But that's a little introduction to fin tabs. Okay? So I'm going to save that. All right, let's add our launch lug. So if you recall last time, stability requires airflow over the fins. The fins need air flowing over them to work. So when this thing, we first light the motor, it's got 0 airspeed. It's got no airflow flowing over the wing or over the fins. So they're not doing anything. We have to keep the rocket flying straight until it accelerates to a point that there's enough airflow over the fins that it can be stable. We can let it go on its own. So the way we do that is what's called a launch lug. So remember, that's that little straw that slides over the launch rod, right? Let's add that in. I'm going to add it to the body tube. I'm going to go up here. I'm going to select launch lug. Click that one time. And that is enormous for this size of rocket. We're going to make it a little more realistic, adjusting the diameter. So let's make the outer diameter, let's see, what would that be in metric? Let's make that 5 millimeters. Okay, that looks a little more realistic. What we just added, again, that's this little, if I can get it on the camera here, this little straw right there. That would have, you can slide that over a rod. As the rocket accelerates, it can, that little straw there can slide up the rod, allow it to accelerate to a point where the fins are effective, and then it can take off on its own. Okay, so that's the launch lug. We'll keep that. Now let's look at a little bit different view here. Right now we're looking at the side view. Let's go over here to where it says view type. You see side view is selected there. Let's hit the drop down and let's see the back view. Now when we look at this from the back, we see we have a problem. So the fin is in the same place as the launch lug. So you wouldn't be able to have a rod go through the fin and then into the launch lug. So we need to fix that. So let's double click the launch lug over here on our parts tree. And we can go down here to radial position. Right now it's at 0. Let's make that 45. Okay, so now we see the launch lug has moved over to the side position. It's not blocked by the fin anymore. I'm going to put that back really quick just so you can see what I did. If you look at this launch lug where it's at now, watch what happens when I change it to 0. Okay, see now it's obstructed by the fin. That's no good. So let's just change that to 45. Okay. And that looks good. Save it. Okay, let's go back to the side view. Again, going up here to the view type, from this drop down, I'm going to select side view. So we've got the basic structure of the rocket. We've got a place to put our motor. We've got the fins. We need to have a way to get it back safely. So if you recall, we talked about a couple different recovery device types, parachutes, streamers. This is what a streamer looks like. This is fine for small rockets, you know, of this size, this very lightweight. It's really just a long piece of ribbon. This is like a piece of plastic ribbon. This is actually preferred to parachutes for small rockets because it's going to minimize the wind drift. So when this deploys up at high altitude, if you're hanging from a parachute and you're descending really slowly, that whole time that it's up in the air, the wind is carrying it away. So this is a faster descent rate, but still slow enough to be safe with a small rocket of this size. Okay, so we're going to put the streamer in this one. So I'm going to add that to the body tube. This list up here has some more options that you can't see right now. If you go to this slider bar, come down to this next couple rows of options, now we see the streamer, right? So I'm going to choose the streamer. Strip length. This one on this rocket that I'm working on right now is about, it's about 50 centimeters. It's about 4. Let's go with 40. And it's about 30 centimeters wide. Okay, so there we go. That's our streamer. That's with it totally unfurled. So that's what's going to come into play after the ejection charge pops it out after it's reached its maximum altitude. So for packed length, though, it's actually going to be wadded up inside the body tube, right? And then when it pops out, it's going to unfurl. But while the rocket's flying, it's going to be all packed up into a little wad. So for packed length, we've got 30 centimeters here. That's totally unrealistic. So let's knock that down. I'll set it at 3. And I'll, right now it's all up in the nose cone. That's not really where it would be. It would be stuffed down into the body tube. So I'm going to bring that down by coming up here to position relative to, again, recall that from top of parent component. I'm just going to add a few centimeters in there just to put it back into a little more realistic location. And the pack diameter, you see right now, it's actually hanging out outside the body tube a little bit, not realistic. So let's bring that down. I'll just knock off a centimeter and make that 1.5. So now you see that it's fitting inside, okay? That looks good. So I'll hit close. Last thing we need for the recovery system is what we call a shock cord. So when the ejection charge, this little small explosive charge that pops out the recovery device, it's going to pop it out with some force. So we want the rocket to fall all, stay together so we can find all the pieces, but we need a way to let that ejection charge force dissipate. We want the momentum to bleed off, but then keep it all tied together. So we have what we call a shock cord. So when this is all assembled in flight, okay, reaches its maximum altitude, and then we need to get the recovery device out. So this little explosive ejection charge fires. It's going to blow the nose cone off and push the streamer out. And so this, what we call the shock cord, which is this, this band here, gives it a way for the energy of the nose cone flying out to dissipate a little bit and not just kind of rip the whole thing apart. So again, this is called the shock cord. Let's add that in. Side note, for small rockets, you might see these kind of looks like a long rubber band. For bigger stuff, we're going to use Kevlar. So Kevlar's it's usually kind of a yellowish looking thread, but very strong and very heat resistant. So it's good for the bigger high power stuff. All right. So let's add in our shock cord. We're going to hit the body tube, click it one time, select that. I'm going to go to shock cord right here, hit that one time. Length, 40 centimeters is probably realistic for something like this. I like a little bit longer. Again, the longer the shock cord you can get away with, the better. It gives it a little more room and time for that energy to dissipate before the shock cord pulls tight. You really don't want it to pull tight. Ideally, when that nose cone runs out of momentum from being blown out, you still want a little bit of slack. What can happen is if you don't have enough length, you can have this come out and get yanked backwards, and then what will happen is this will pull down the side and cause what we call a zipper. It'll actually rip its way down the side of the tube. So a longer cord is better. All right, so I'm going to make mine a little longer. Let's go with 50 here. And again, the packed length and packed diameter. The packed diameter right now is larger than the body tube. That's not realistic. Let's make it fit inside. I'm going to reduce the packed diameter Just knock off a centimeter so that it fits inside. And the position is actually going to be back behind the streamer because it's going to connect. Usually it'll either glue to the inside of the body tube or it is tied around the forward centering ring, which is the preferred way. It's more secure. So I'm going to move that back behind the streamer where it's a little more realistic. So for the position relative to, I'm just going to add some centimeters in there. You'll see that moving back and it's behind the streamer now. So that's where we want it. That's realistic. Okay. So I'm going to close that, save it. So at this point, we have the workings of a functional rocket, right? We've got the airframe is all here. The motor mount is here. We've got a way to attach it to the launch pad, and we've got a recovery system, a way to get it back safely. So let's put a motor in it. We're going to move over to the next tab here where it says Motors and Configuration. All right, so we're going to go to New Configuration. And now, keeping in mind, this software is kind of designed for, here in the US or, probably users in Europe, Australia. These are mostly motors that are commercially available in this database are what's available here. That's not to say that you can't add custom thrust curves in here if you have them. You certainly can do that. But I'm just going to walk you through the steps showing some stuff that's commercially available already here in the database so we can run some simulations. But to reiterate, you can add thrust profiles into this software that aren't here. There is a provision for that. But let's go to New Configuration. So this was, when I very first started this was something that I found a little bit, non-intuitive to figure out how to get a motor to show here. So when we first hit New Configuration, we get this first list. It's got configuration, it says no motors, and it's for the inner tube, it's got none. So we haven't selected anything yet. So where's the list? How do we find the motor? Okay, so there's a couple ways to do it. You can either come down here to where it says select motor and click that, or you can double click where it says none. Either action will bring up the database of motors in the software, okay? So I'm gonna click select motor one time. Here I get this list. Now we can whittle down the database to what is appropriate for the rocket that we're flying. Now, one thing we know, we already talked about, is our motor mount is 18 millimeters in diameter. And I see they've already got this, this is still showing up in inches, but we can select that. We can use these sliders to reduce it to what we want. Okay, so there we've knocked it down to 13 millimeter diameter motors and 18 millimeter. We can refine that a little further. Even we can take this slider bar, move it over. So now we've got our database narrowed down to only motors that will fit the rocket. We've selected all the 18 millimeter motors that we have available. Okay, this one that I have here, it's a brand called SEDS, and it's a C65. So if you recall from last time, the C tells us the total impulse. So that is the thrust in newtons multiplied times the time, the amount of time in seconds that the motor can maintain that thrust. So that gives us what we call total impulse with a unit of Newton seconds. So those total impulse ranges are classified by letter, and we see this motor is a C impulse motor. The 6 tells us that the average thrust is 6 newtons, and the 5 tells us that the ejection delay for the parachute is 5 seconds. We'll talk about a little more about that when we talk about the simulation, but that's what the 5 means. So I can find this on this list. This is the SEDS C6. I'll highlight that. So where it says select thrust curve, it's gonna, for the purpose of the simulation, it's gonna use the thrust profile from this C6 motor, okay? So it's got the thrust curve as C6. And the ejection delay, right now it's at 0. Remember, that's the 5 seconds, right? That comes from the side of the motor here. That's the -5. That tells us the number of seconds for the ejection delay. So I'm going to choose 5. Okay. So I've got my motor selected. I've got my delay selected. I'm going to hit OK. And now it has, you see in the motor mount, it's dark gray. It has put the motor in there. So now that we put the motor in there, we see the center of gravity has shifted back quite a bit, which has a destabilizing effect, right? So we added a lot of mass to the back of the rocket. From a stability standpoint, that's not good. Right now, our stability over here, we're seeing at 0.852 calibers, probably would fly fine, but I'd rather see it at least 1. We can change the stability by either manipulating the center of gravity or the center of pressure, right? If I want to change the center of pressure, I can play with my fins a little bit. So I can, double click my fins. I'll go to shape. I can, maybe make them a little bigger. See, I just added a little bit of fin area. Now I'm at above 1. Or I could make a 5 fin design. That made it even a little more stable, right? That's one way to do it. If I needed to, I could also shift this. So that was a way to shift the center of pressure. If I wanted to shift the center of gravity, maybe I could add some weight to the nose. So like I'll double click the nose here. Let's go back to rocket design tab. Again, I'm back up here in the top, going back to rocket design. If I select the nose, I'll get some options available to me. You see this one called mass component. That's kind of a useful one if you're doing design. If you just want to put like a generic mass in there that's not otherwise listed, it's a good one to know. So I'm going to click mass component, and I get this mass. I'm going to move it back by changing the position. I'm going to go to position relative to, move it back inside the nose so it's a little more realistic. Change the length and diameter a little bit so it fits inside the nose cone. For little small rockets like this, what you'll usually use for nose weight is just like a little piece of clay, and you can pack it in there. It'll stay just fine for the kinds of forces that we're dealing with these smaller rockets. Just like a little piece of clay packed in there, works fine. Maybe add a few grams of clay. I'm going to change the component name to nose weight. And you'll see that reflected over in the parts list on the left. Okay. And now for mass. So you'll see as I add mass to the nose, I'm shifting the center of gravity forward, and that's going to increase the stability. So watch as I add some mass. If you watch the stability, which right now is at 1.12, I add some mass, it's going to get more stable. All right, so as I add a little mass there, we see it getting more stable. I don't really need that there. I was already at 1 caliber without it, so I'm going to take it back out because it's unnecessary weight. It's going to cost performance, but that option is there if you need it to make the rocket stable. So again, I'm going to set that back to 0 just because we don't need it, but now you know how to do that. If you want to move the center of gravity forward, you can by adding some nose weight. Also, if you make the body tube longer, that's also going to shift the center of gravity forward. So a longer rocket is going to be inherently more stable than a shorter one. That's an option for you too. All right. So let's save that. So we've got our motor in place. We've got the stability margin is what we're happy with. It's between 1 and 3. Sounds good. Let's run a simulation. So I'm going to come over here to flight simulations, right? This tab right here. And I see I've got our only motor there selected so far is the only one that we have installed from the database is the C65. So to run the simulation, I can just highlight that by clicking on it once. Now you see that row is blue, and we can go to run simulations. We'll click that right here. So the software is going to run some numbers and tell us some very useful things, okay? So velocity off rod, that's an important one. Remember, we need the rocket moving fast enough that it has plenty of airflow over the fins to be stable before it leaves the rod. So that's an important one to know. It's going to tell us it will reach 317 meters in altitude. The velocity at deployment, that means, so as the propellant is burning, the rocket is creating thrust, it's accelerating. At the point that the propellant runs out, the rocket's going as fast as it's going to go. As soon as the propellant runs out, gravity and drag or air resistance are going to start slowing it down. Eventually, it will reach a point of 0 vertical velocity and then start coming back down. So this is telling us the velocity at deployment is 10.1 meters per second. So remember, in this motor, we had a 5-second delay between the time the rocket runs out of propellant and the time that it fires the charge that deploys the streamer, okay? So this is an important one. If any of these are kind of like outside what the software has set as safe parameters, this green check mark over here will be a red exclamation point. So it's telling us that these are all, parameters that the software is happy with at this point. Optimum delay, this is a really useful one. So if we have all these motors and they've got these different delay times, some of them come with 3 seconds, some of them come with 14 seconds. How do we know what we want? Okay, it's telling us the optimum delay, right? That's the time between running out of propellant and firing the recovery system is 5.84 seconds. And this motor that we selected has 5 seconds, pretty close, okay? Again, if the software doesn't like the way it's turning out, it will give you a red exclamation point over here. And if you hover over that red exclamation point, it would say recovery device deployment at high speed. In other words, going too fast through the air, a lot of forces on the rocket when the parachute or the streamer pops out, gonna rip the thing apart. Doesn't like that. So in this case, 5.84 seconds is what it's calling optimum. We have 5 seconds, close enough according to the software, okay? It tells you some other fun stuff, the maximum velocity that it reaches, the maximum acceleration, other interesting things, total flight time, and ground hit velocity. That's another important one. So especially when you get into the bigger, heavier rockets, you want to make sure that you have your parachute is big enough. And that's where the software can help you out with that, evaluating is the ground velocity appropriate? Is the parachute big enough? Okay. So that is the gist of it. That's the basics. That's how to go from, nothing, from scratch to we've got our first working model. Okay. Let's look at a little plot of the data for this one. We're going to go up here to plot and export. Okay. So there are some parameters that we can manipulate in here. A useful one is we can change the length of our launch rod. So if we have our actual launch pad with our rod or rail, we want to simulate that accurately. Again, remember the length of the launch rod is a critical parameter because it makes us able to let the rocket accelerate to a safe speed before we let it go on its own, right? So typical launch rod is probably about 3 meters, or excuse me, about 1 meter. So I'll change that. And we'll go down to simulate and plot. So here's our simulation. And these are some of the basic things that the software can spit out. I'm gonna go back a step just to show some options, but where it says y-axis types, we've got a lot of different things we can evaluate with the software. Right now it's set up to display altitude, vertical velocity, and vertical acceleration. But if we hit these drop downs, there's like tons of stuff we can play with. It's a little beyond the scope of this kind of entry level talk here, but just be aware that there's a lot more that the software can do than what we're talking about today. So let's go back to plot and just evaluate some of the things that it's telling us. So one is altitude, okay? How high did it go? So that's the red track. If we follow that up, we can see that I think it said we got to around 310 meters, something like that. But we can see that altitude on the y-axis here. Some of these things that are indicated by the vertical lines. Okay, we've got the motor ignition, the motor burnout. That's where the motor ran out of propellant. Now you see at motor burnout, that occurred at only about less than 2 seconds into flight. But then the rocket has a lot of vertical velocity. It's got momentum. It's going to continue to coast upward until gravity and drag stop it. So we see that the time that the rocket is under thrust is actually a pretty small part of the time that the rocket is going higher in altitude, right? So it burns out at about 2 seconds, continues to coast upward, doesn't hit apogee or maximum altitude until almost 8 seconds, right? So the motor's burning for 2 seconds and it's coasting upward for about 6 seconds. And then it's on its way back down. Oh, we've also got vertical acceleration and vertical velocity plotted there. So let's briefly talk about staging. I got a lot of questions last time about multi-staging. If you don't know what that is, it's we can have multiple motors in a rocket set up in series vertically. So we'll have a booster stage or a booster motor that burns first. When that one runs out of propellant, it will actually fall off to get rid of unnecessary weight. And then it will ignite the second motor, like the upper stage or what we call the sustainer. That'll keep on continuing upward. Okay, so let's look at an example of that. So here's how this kind of works with a small rocket. Okay, this is for black powder motors only. This doesn't work with the ammonium perchlorate composite motors that we talked about. But for this type, the black powder, they're easy enough to ignite that this will work just with this very simple setup. So we can have what we call a coupler. It's just another little cardboard tube that goes inside the outer tube. So the outer diameter of the coupler is the same diameter as the inner diameter of the main tube, right? And it can just slide into the back of another rocket. And it's just kind of friction fits. It's just in there just snug enough that it won't fall out, but it's not attached. It just pulls right out, okay? So we could have our booster motor in this rocket, keeping in mind for a booster motor, right, where we had the C65, the 5-second ejection delay. In a booster motor, it would be C60. There's no ejection charge. It's just going to burn the propellant up, and then it will just burn right up into the next sustainer motor above it. Okay, so this would be a C6-0 if it was a booster. So again, that just slides in here. So we would ignite that booster motor. It's these little black powder motors are in what's called an end burner configuration. So the propellant burns from bottom to top or back to front, however you want to look at it. When the propellant burns up to the top in the booster stage, that will ignite the sustainer or the upper stage. That pressure will just knock the bottom off, and then sustainer happily goes up on its merry way. I mentioned vent holes last time. If you'll notice, there's a little hole opposing on each side. That's to allow the cold air inside to vent out. We need the hot, burning, little pieces of propellant to fly up and ignite the upper motor. So we need to allow the cold air to vent out. So that's what these two little opposing holes are for. But again, this will just, the bottom motor burning up will ignite the top motor. That thrust will knock the lower stage off, and it'll continue on up. So with the black powder motors, it's super simple. But let's just see how that applies in open rocket, how we can simulate it. Okay? So let's go back here to rocket design. And there's a question in the chat. Let's see what that there. Is software using turbulent models? You can, let's look at that real quick before we move on to the staging. Let's go back here to where it says flight simulations. And I've already got that highlighted. I'm going to go to plot export. And let's go to edit. And here it's got turbulence intensity at 10% or medium. Yeah, you could play with that. You could change that. Here we've got a little note. Turbulence intensity is the standard deviation divided by the average wind speed. Typical is 5 to 20%. I mean, if you wanted to be conservative, set that up to 20%, and that's going to be reflected in the simulation. In reality, remember, we said always safety first. So if it's really windy, you've got a gusty day, you probably want to just not fly that day. But yeah, the software does have some provisions for adjusting turbulence. So that's right here where it says turbulence intensity. You could, play with that. All right. So let's go back to talking about adding a stage. So we're going to go back. Let's see. Thanks. You bet. No problem. Let's go back to rocket design. We're going to go here to where it says new stage. So remember, I went back to the rocket design tab. Click new stage. We're adding the booster stage. Let's check out where it says separation. Now this is going to kind of depend on, remember we talked about there's black powder motors, which are the really easy ones to ignite. And then there's ammonium perchlorate motors, which have a lot more specific impulse or power per unit weight of the motor. But they're a lot harder to ignite. So this staging is not nearly as simple when you get into the ammonium perchlorate propellants. But since we're dealing with, kind of a basic black powder motor here, that's how we're going to set this one up. So select when this stage separates. Upper stage motor ignition. Basically, like we talked about, as the booster motor burns up, as soon as that conflagrating propellant makes contact with the upper motor, it's going to immediately kick it off, and it's going to just knock the bottom stage off. So that's already set how we want it. We could, however, if we had a more complex system, we're running ammonium perchlorate composite motors, we're using electronics with a battery that's riding in the rocket, on board the rocket, to provide the ignition source, we can manipulate this if we need to. So we have, drop down. We can index it to a certain amount of time after the lower motor burns out. That's usually how you would do it. So just know that those options are there. It's a little more advanced, but we're going to leave it as it is. Right now, it's the stage is going to separate when the upper stage motor ignites, because the upper stage motor ignition is what's going to knock the bottom stage off. Okay, so that's happy. So we're going to close that. For the booster stage, let's remember we've got this parts list here that we can not see it all at the same time, at least the way I've got mine set up. Going back up here to where it says body tube, I've got booster stage highlighted over here in the parts list. I'm going to select the body tube, and you'll see that it's added this body tube down underneath the sustainer. So we've got a booster stage body tube now. That's like kind of ridiculously long. I'm going to configure it something a little more like this. So let's take the length, knock it way down. Okay, that looks fine. Remember, we had the little coupler that slides in there. So there's the little smaller diameter tube that allows it to slide into the upper stage like that. We'll add that in. Let's see what's going on with the chat here. Bit more about the separating force given by the motor. Sure. So in this case, let's imagine. So we've got, let's look at our upper stage. I'm going to put the motor in there in our upper stage, right? So this is going to just slip right over it. So if you imagine now, if I had another motor and there was one in there, when this upper stage ignites, the thrust coming out of this upper motor is basically just going to knock this off. Now, in larger rockets, sometimes we'll have a little explosive charge there. So in bigger rockets, we'll have what are called shear pins. They go in the sides. It's just like little plastic pins that go through to hold this securely in place. But when the upper motor fires, it's going to need some help to actually break those shear pins. cuts the pins in half. And sometimes there will be a little explosive charge in here that pops it off, okay? But in this case, it's just, as this upper motor ignites, the thrust coming out is just gonna push this right off, okay? Explain a bit more about the separating force given by the motor and what triggers the explosive charge. Okay, so again, in this case with the little black powder motors, just the thrust coming out. So this motor is going to start burning. Hot exhaust gases are going to be coming out at a very high speed. That's what's propelling the rocket upward. That's the thrust. It's also what's going to just, you know, again, this is just in here loosely. Held in with a little bit of friction. I mean, I can shake it, it doesn't fall off, but I give it a little bit of pull, it just falls right off. So again, it's the thrust from the upper motor that's just pushing this away. Now, in a more advanced setup, again, with the ammonium perchlorate composite motors, you're gonna have electronics in here that's controlling all those functions. So the electronics are monitoring things like acceleration with an accelerometer, barometric pressure with a pressure sensor. So it's detecting changes in altitude, it's detecting changes in acceleration. It's also measuring time from the liftoff detection. It can detect when the rocket is lifted off. It's got, you know, again, monitoring barometric pressure changes, because right as you go higher in altitude, barometric pressure decreases. So the computer can detect all these things. And you've got it pre-programmed and configured so that all these things are timed correctly. That's a more advanced, you know, setup. But again, these little black powder motors are great for starting off because they're just dead simple. They're really easy to light. But some of my favorite parts of rocketry are getting into the electronics and getting into the complexity. So that's a good, really good question. Yeah, that's all controlled by electronics, and there are batteries on board riding with the rocket that provide the voltage to perform all these functions. So that's a good question. All right, so let's go back to our booster stage. Remember, we need to put a motor in it. Let's put our motor mount in it. I'm going to start going a little bit faster, so you know, stop me if you need to. Let's put a motor mount in it, very similar to what we did in the upper stage. I'm going to select the body tube. I'm going to put an inner tube. Remember, we need to designate that inner tube is a motor mount. So we're going to go to the motor tab, check that. Motor mount box. We just told the software that that's a place that we can install a motor. All right. Let's pop some centering rings in there. Make them the correct diameter so they fit up against the inner wall of the body tube. We can securely glue it in place, right? Move it up to the front. Okay, I'm gonna add another centering ring by just, I'm gonna copy it, paste it. And again, I'm gonna change the position. Right, so now we've got two centering rings in there, keeping the motor mount aligned with the rocket and also have it secured so the thrust doesn't just blast the motor right through the rocket and then got all kinds of problems, right? So we've got our motor mount there. Let's add some fins to the back. Remember, we're adding another motor all the way in the back. We're adding mass to the back. That shifts our center of gravity back. That's a destabilizing effect. We need to make sure we compensate for that. So I'm going to add some fins to the booster section. I want to shift my center of pressure way back. I want to put fins as far back as I can. So let's add some fins there. I'm not going to play around with it a little bit. I'm just, you know, making a point here, but leave the fins like that. Kind of crazy looking, but it serves its purpose, right? Now, let's save that. Now, if we go back to motors and configurations, we have a little more to play with. So we have, right now it says C65 and none because we haven't selected a motor for the booster yet. But we've got two places where we can install motors now. Because remember, when we installed that inner tube, we designated it as a motor mount, and we've got multiple motors that we can install now. So let's go to this. We're going to select where it says none. We can either click select motor, or we can double click where it says none. We've got our list. I'm going to use another C6, and the delay is 0. Remember, when we're using the booster motor, it would be like C6-0 instead of C6-5. There's no ejection charge in the booster, right? It's just going to burn right up into the sustainer motor. All right, so move this so I can get to it. Okay, so now we have a motor in our booster, and we have a motor in our sustainer. All right, so we've got the C6-5 and the C6-0. Let's play with our simulation a little bit. So let's go back to flight simulation. And we see our configuration now is C6-5 and C6-0. Let's highlight that. We'll run the simulation, see what's going on. We've got a warning here, recovery device deployment at high speed, right? So again, that's where you could play with your delay, your optimum delay. It's got it at 5.8 seconds. The factory commercially available one for the C6 usually comes in ejection delays of 0, 3, 5, and 7. You can play with different delays, see what you get. Let's plot this one. All right, so now this is cool. We see something that we didn't have before. We've got motor ignition. This vertical line shows us motor burnout. That's the booster running out of propellant. Motor ignition, that's the sustainer motor igniting, and stage separation. So that occurs right here. And we see two diverging red lines. So we've got the booster coming up to this point and then separating and falling off. And we can see that its momentum actually carries it upward a little bit before it starts taking a dive. And then the sustainer continues on upwards, right? And then again, we get our recovery device deployment. We get our apogee, which is the highest altitude we get. And the rest of the rocket. We get our ground hit for the booster here and our ground hit for the sustainer over here. All right. So that's the gist of it. I mean, that's everything you really need to know to get started. We talked about how to, enter in all your dimensions for the pieces, enter the density of the materials. The really important thing that the software can really help you out with is determining where's the center of gravity and where's the center of pressure. What's my stability? Is this going to be a safe rocket to fly? When I run my simulation, safety critical parameters. What's my velocity when it leaves the rod? Is my ejection charge time correct? Is my ground hit velocity safe? So remember, when we ran all the simulations, it told us all those things. So really good software for evaluating your rockets for safety. Are they going to fly well? Tweaking little different safety critical and flight parameters. Real quick, gonna just show you a little bit of the more like fun part, but if we want to, kind of get a feel for what our paint job is going to look like, if we choose different colors and things, we can get a feel for that using the software. So I'm going to go back to rocket design. And I'm going to select a part. So I'm just going to go down here to my diagram. I'm going to double click a part. And I'm going to choose this tab that says appearance. And we can start playing with colors and things and looking, getting an idea of what different paint jobs would look like before we actually do it. So right now here where it says appearance, it's got a check box by use default. I'm going to uncheck that. And when I do that, you see the color hatch here becomes available. Default is black, but if I click on that black rectangle, I get all these color choices that I could play with. So for right now, I'm on the nose cone. I'm going to just pick a color. I'll say blue. And I can turn the shine up. So if I painted it with a nice glossy finish, I can reflect that. I'm going to turn my shine all the way up. All right, now, so I made the nose cone blue, but I don't see anything different yet. But if I go to view type, go down to 3D finished, it'll start showing me these changes. So I made the nose cone blue, but it still shows the other parts in their bare materials. So bare cardboard, bare wood, whatever materials we selected, it's just showing us what that looks like. Okay. So another useful view when you're doing things that are a little more complicated is this 3D figure. I really like this one. It shows you how all the internals fit together. If you're doing something a little more complex, you need to figure out sizes and things, see if things are going to fit. That's a useful one to know too. But let's go to 3D finished. Again, I can double click a part, get this window come up. I'm going to go to the appearance tab, uncheck use default where it says appearance. I'm just going to pick a whatever color just for demonstration purposes here. Same thing with the other parts. I can just double click the part, get that window, go to the appearance tab, uncheck use default, boom, pick a color. Okay, so you get the idea. I mean, you could go through that through the whole thing. We can also play around with some little bit of visualization. If we go up here to tools, this one's kind of fun. Go to Photo Studio. So I went to Tools, Photo Studio, and you know, I can kind of play around with it, make a nice visual of my design. I can, you know, move it around by adjusting the view distance. I can, you know, make it look farther away or closer. If I go to environment right now, it's flying over some mountains. I can have some different backgrounds. You know, sky image right now is mountains. I can choose orbit. All right, now it's up in orbit. Cool, right? Effects, I can add, you know, flames. So there I made a little, you know, flame from the motor. I can play with the color, the size of the flames and all that. So, you know, if you just want to make a nice little visual of your design, this is you can do it. All right, so that's kind of the fun part, but really to reiterate, the real value of the software, at least in my mind, is safety, right? I can look at stability. I can look at, do I have enough thrust? I can look at, do I have the correct ejection time delay for my parachute or my streamer? How's my ground hit velocity looking? That's really the value of the software. Getting all these things figured out before you commit to, you know, cutting your fins out, using materials and gluing things together. Okay, so that's the gist of it. We just designed a basic small rocket, ran the simulations. Again, there's a lot more you can do with it, but that's a good introduction to the basics. So that's what I have for this morning for you. But let's open it up to some questions. And I realized this time we were kind of asking questions as we went along. So there may not be very many, but I want to give people the opportunity to ask if they have them.
Guys, you can type your questions in the chat, or you can ask questions from Mr. Frizzell directly. And there have been some direct messages to me, but most of those questions were answered during the session.
Okay, good.
As we went along, the Q&A session kind of blended into that, I think.
Okay.
Any new questions? Yes. Oh, there's one question asking whether we can use rocket motors together, as in 2 or 3 motors at the bottom, and, you know, light them. What?
Yeah, sure. Yeah, let's do that. Tell you what, I'm gonna to kind of facilitate that, I'm gonna delete this booster, and I'm gonna make this bigger. so we can fit more motors in there, right? And this is called a cluster. Yeah, you can definitely do it. It's a little more advanced. It takes a little bit of, there are some considerations to make sure that all the motors light at the same time. If they don't all light, you end up with asymmetric thrust. And if you don't have your design, if it's not designed well, and you don't get all the motors lit and you have asymmetric thrust, it comes off the launch rail and starts doing loop-de-loops, and that's no good. But yeah, you definitely can do it. We do it all the time. I'm going to make the diameter bigger, and this is going to look ridiculous, but just for the sake of demonstration. So our nose cone is completely stupid, but let's go to where it says inner tube. Remember, when we selected our inner tube, we click the checkbox, designate it as a motor mount, right? So to make it a cluster or have multiple motors that you can ignite at the same time, we're going to go to this cluster tab right here. And this gives us a bunch of different configurations we can choose one. So let's say we want to put 3 in there in this configuration, right? I can have them there. Select that one. Tube separation would be like, so if you have your multiple motor mount tubes in there and you want them, a little bit apart, you can manipulate that with the tube separation. And rotation, you can change how they're oriented inside the rocket, inside the body tube. Split cluster, you could do that if you wanted to have like different motors in the same cluster. Just keeping in mind, you'd have to have equal thrust opposing, so you don't have unbalanced thrust. But like if you wanted to, you could have, say, a 5 motor design with a powerful one in the center and smaller ones on the, the 4 on the outside. Yeah, there's like tons of different permutations you could do with it. A lot of fun you can have with that. But I'm going to make the nose cone kind of the correct size because it's sort of driving me nuts here. Still looks ridiculous, but we'll go with it. And let's look at it from the back now. So now you see we've got multiple motor mounts in there that we could put a cluster and ignite them at the same time. Another little pointer for that, more motors needs more voltage from your battery to ignite. So again, there are some little know-how things that go with clustering. It's a little more advanced technique, but yeah, you can definitely do it. I'll just go back and recap that real quick, how I did that. I went to the inner tube that I had designated as my motor mount, open that, and you can make those changes in the cluster tab. Okay, that's how I did that.
Any new questions, guys?
Okay, well, gang, it is midnight for me here. So if there's no further questions, I'm going to bow out, but thank you for joining us. And I have fun doing these talks. So I love talking rockets, and it's great to have a captive audience. So I appreciate you joining me.
Yeah, thank you, Mr. Frizzell, and we are extremely grateful that you joined us not only once but twice. And to be honest, it's almost like your level of enthusiasm is almost parallel to us. So
Well, good. I'm looking forward to seeing some builds out of this group. I'm very eagerly awaiting, where this goes. So
yeah,
I'm excited to see what you come up with.
Yeah, we are excited as well because there has been some people asking about where to source materials and so on. So
Right. And again, when you're starting out with these low power ones, it doesn't have to be fancy. You can be,
yeah,
rolling the tubes out of like a heavy duty paper, like a cardstock, you can, this is just a cardboard tube, like a thick cardboard tube. And these fins on this one, it's really like a thick paper card. I mean, it's really not, it's nothing fancy. The nose cone, I've seen people carve this out of wood, for this little stuff, getting started. You can have a lot of fun with these little ones getting started, and it doesn't have to be really, really fancy. I'll point out this too. We talked a little bit about tube fins. This question came up last time. Someone asked, like, hey, I'm making this design and it's going like almost supersonic and I want to slow it down. How can I slow it down? And I suggested tube fins is a very draggy design. So this is actually like the fins, instead of having like a wing, like, let's get this untangled. Instead of having like a wing shaped fin like this, like a flat protruding fin, you can actually just take some sections of tube and glue it on around the circumference, and that will behave as fins. Like if you get this tube part figured out and you can cut some little sections of tubes, that's very adequately going to serve the purpose of shifting your center of pressure back. That's what we need for stability. This is actually a very stable configuration. So maybe a little more simple depending on what your materials limitations are, but that's an option.
Okay, guys, then it seems there are no new questions. So shall we wrap it up? Yes. For us, it's the beginning of the day, but for Mr. Frizzell, it's the beginning of the day in a very different sense, as in midnight.
Hey.
So, Mr. Frizzell, thank you, and I hope to be we hope to be in touch with you. And I think there's a vote of thanks prepared by Hassan. You there? Can't find it. Hi.
So today's session was another wonderful session, like the previous rocketry sessions that we brought to you. These rocketry sessions are present to you by SEDS SLTC in collaboration with SEDS Mora. So now it's time that we all have to wrap this up. First of all, I would warmly thank Mr. Josh Frizzell for coming here and sharing his knowledge, even in his busy schedule, and not once, but twice again today as well. And next, I would like to thank all the people who collaborated to work to this. And last but not least, I would show my heartiest gratitude to all the viewers, participants who are here today to make this a success. Hope everyone would have gained a fruitful session today, and hope to see you all again, once again, through another fruitful session like this once again. So have a good day.
Thank you all.